welcome to the chemistry channel. So today we're going to be talking about atomic size or atomic radius. So the first thing that I want to do is to do two different thought experiments. So in this first thought experiment we have two different atoms with two different charged nuclei. So in the first atom we have a +1 charged nucleus, and in the second atom we have a +2 charged nucleus. So which distance, D1 or D2, do you expect to be larger? Well, the larger distance would be expected to be from this atom. And that's because you have a +1 charged nucleus compared to a +2, which means that it has a weaker force of attraction. So it has a weaker force of attraction. So this means that this nucleus is not pulling in the electron as strongly as this nucleus. And since this nucleus is not pulling in the electron as strongly, the electron can exist at greater distances. So let's move on to the second thought experiment. So we have two different atoms here. In this case, we have both with a +1 charged nucleus. However, in case number 2, this little green dot represents another electron. And this is and the black electron is the electron of interest. So which distance do you expect to be larger, D1 or D2? Hopefully you said D2. And the reason why is because you not only have this attractive force from the nucleus, but you also have a repulsive force coming from this electron. So therefore, the repulsive force subtracts from the attractive force, making the net attractive force on this electron, on our electron of interest, smaller than that of this atom right here. So therefore, D2 will be greater than D1. So we can use these generalized ideas in order to describe an atom's atomic radius. So what is an atomic radius? Well, the atomic radius is the distance from the center of the nucleus to the periphery of the atom. So if we symbolize an atom like a circle, and our little dot here is the nucleus, the atomic radius would be this distance. So this would be the atomic radius. So it basically tells us how large our atom is. So what are the general trends of atomic radius on the periodic table? Well, the general trends are this. As we move from left to right, the atomic radius, so this means atomic radius, tends to decrease. And as we move from bottom to top, the atomic radius also decreases. However, as we move from right to left, the atomic radius increases. And as we move from top to bottom, the atomic radius increases as well. So those are the general trends that you need to know for atomic radius. However, why? So why do we see these trends? So let's look at the first trend. So as we move from left to right in a period, atomic radius tends to decrease. So why is this? Well, it's because atomic radius is correlated to the effective nuclear charge. And as we move from left to right, the effective nuclear charge increases. And this is left to right on a period. And as effective nuclear charge increases, the force of attraction exerted on the outer shell electrons from the nucleus increases as well. Now, this increased force of attraction, so this force of attraction, causes atomic radius to decrease. So that's why that as we move from left to right on the periodic table, the atomic radius tends to decrease. Now the second rule was from as we move from top to bottom in a group, atomic radius increases. Well, why? Well, this is because as we move down a group, the principal quantum number increases. And as the principal quantum number increases, the probability of finding an electron, so this means an electron further from the nucleus, increases as well. So this means that atomic radius increases as we go down a group. So those are the two explanations for the two main rules. So what about ions? How do ions come into play? Well, let's first talk about cations. So here we have a neutral sodium ion, a neutral sodium atom, and a sodium cation. So remember, this is a cation. And remember that cations are formed by the loss of electrons. So note that ions are formed only by gaining or losing electrons. The atomic number does not change. The only thing that changes is the amount of electrons. So let's write the electron configurations for both neutral sodium and the sodium cation. So neutral sodium has the electron configuration of the neon noble gas core with one electron in the 3s subshell. While sodium plus 1, or the sodium ion, has the electron configuration only of the noble gas neon. So which one of these species here do you think will be bigger? Well, the neutral sodium will be bigger. And this is because when you take electrons away, to form a cation, you do two things. So the first thing that you do is remember that you take electrons away from the highest principal quantum number. So therefore, as you take electrons away from the highest principal quantum number, your probability of finding an electron in further distances from the nucleus decreases. Also, you decrease electron to electron repulsions because you're taking away electrons. Therefore, cations have a smaller atomic radius than their corresponding or than their parent atoms. So that's the rule for cations. So now let's look at an anion, and here we have fluorine and fluoride. And remember, this is an anion, and that's just a negatively charged atom where we add electrons to the atom. So let's write the electron configurations of both of these. So fluorine has the electron configuration of the noble gas helium with 2s2, 2p5. However, when you do fluoride, you get the noble gas configuration of helium, 2s2, and then 2p. So you have more electrons in the fluoride ion than fluorine. So what do we get from forming this anion? Well, you get more electrons. And when you get more electrons, you get more repulsion. And when you get more repulsion, you get increased size. So therefore, the atomic radius of an anion is larger than the atomic radius of its parent ion. And that's the rule for anions. And that is it for the material for today. So here I have 2 practice questions. So try these for yourself, and when you're done with them, come back and we'll do these together. So hopefully you did these practice questions and came back and are watching this now. So let's do this first one. So remember that atomic radius increases from right to left, so atomic radius increases from right to left and from top down. So therefore, by using those trends, you see you can rank these by increasing atomic radius. You will get carbon, boron, and aluminum. So aluminum would be the largest, boron would be in the middle, and then carbon would be the smallest. So the next one is a little bit trickier. So in this one, the best way to do it is to see how many electrons are in each one and to rank them accordingly. So it's important to note that all of these are isoelectronic. So what does that mean? Well, isoelectronic means that they have the same number of electrons. So they have the same number of electrons. So all of these, if you go through each and every one of them, have the electron configuration of krypton. So therefore, we can use the charge in order to rank the size of these. So strontium 2 plus would be the smallest. Then rubidium plus would be the second smallest. Then bromide, and then our last one. And this would be increasing atomic radius. And that is it for the video today. I want to thank you all for watching, and I hope to see you next time. And please post any questions that you may have in the comments. Thanks, guys.